In our next example, we're going to work our recursive sequence a little backwards. So here goes. You're saving money for retirement and you plan to withdraw $30,000 at the beginning of each year for 10 years after you retire. Based on the type of investment you're making, you are expecting that you're going to earn an annual return of 8% on your savings. Let A sub n be your balance after n years after retiring, and write a recursive equation that shows how A sub n is related to A sub n minus 1. Solve the equation from part A for A sub n minus 1 and find A0, which is the minimum amount of money needed in your account to retire. A sub n is related to A sub n minus 1 with respect to the annual return that you get. So it's going to be 1.08 times that A sub n minus 1. But after we have withdrawn $30,000 at the beginning of the year. So this is our rule, and this rule we now need to solve for A sub n minus 1. And the way we do it is we add 30,000 on both sides, and we get A sub n plus 30,000 is equal to 1.08 A sub n minus 1. And now let's divide both sides by 1.08. And this is how we're going to get our A sub n minus 1. And now we're going to use this rewritten rule to go from our last amount, which is A sub 10, all the way back to A sub 0. Now A sub 10 we're going to assume is equal to 0. We have withdrawn money for 10 years, $30,000 each, and then we're done. There's no more money left. So then A sub 9 is equal to 0 plus 30,000 divided by 1.08, and that is equal to $27,777.78. Now we're going to use the amount for A sub 9 to find A sub 8. So A sub 8 is going to be 27,777.78 plus 30,000, all divided by 1.08, and that is $53,497.94. Alright, you guys, now stop the video and find the rest of the values yourselves. A sub 7, A sub 6, and so on, all the way back to A sub 0 are beginning amount. I said stop the video. Alright, here we go. Hopefully you came to the same result as I did, and I apologize, I had to squeeze some numbers in here a little bit. You had hopefully some more room on your note page. The total amount you need to start is $201,302.44, and that's not so bad really if you think about wanting to withdraw $30,000 for 10 years in a row. 30 times 10 is 300,000. You only need to start off with 200,000, and that is because of the interest that you earn each year on the remaining amount. Still, $200,000 is a lot of money, so you better start saving. So what is the Fibonacci sequence? The Fibonacci sequence is probably the most famous recursive sequence, and the way it's built is following this rule. A sub n is equal to A sub n minus 1 plus A sub n minus 2. So we have to add the two previous terms to get to our new term. That means we need to have two terms to start with, and those two terms are A sub 1 is equal to 1 and A sub 2 is also equal to 1. Let's find some terms to get a feeling for this sequence. A sub 1 is equal to 1. We said that A sub 2 is equal to 1. That means that a sub 3 is equal to 1 plus 1, which is 2. A sub 4 is equal to 1 plus 2, that is 3. A sub 5 is equal to 2 plus 3, which is 5. A sub 6 is equal to 3 plus 5, and that's 8. A sub 7 is 5 plus 8, that's 13. A sub 8 is 8 plus 13, 21. A sub 9 is 13 plus 21, which is 34. A sub 10 is 21 plus 34, which is 55. A sub 11 is 34 plus 55, which is 89. And a sub 12 is 89 plus 55, and that is 144. And we could keep going and going and going. So, what's so special about the sequence? Let's do this. Let's take a ratio of each term with the previous term and see what happens. Then we have a sub 2 divided by a sub 1. That would be 1, right? A sub 3 divided by a sub 2 would be 2 over 1, or 2. A sub 4 divided by a sub 3 would be 3 over 2, which is 1.5. A sub 5 divided by a sub 4 is 5 over 3, and that is 1.66. I went ahead and calculated a few more of those ratios for you, and if you look at this, you can see that the ratios oscillate, they go up and down, but they get closer and closer to a specific number, which they almost reach then at the end. And that number is also a very important number, 1.618. And that is called the golden ratio, and it's also called phi, using the Greek letter phi, either the capital or the small one, and that is approximately 1.618. It's not exactly 1.618, it's a never-ending decimal, but this is a very important number, and what is so important about it you will see in the next video clip that's coming right now.
The easiest place to find these numbers in nature isn't in bunnies, it's in plants. If you cut a banana into slices, you'll see that it has 3 distinct sections. An apple has 5. No matter what kind of flower you're looking at, chances are it has 3, 5, 8, 13, or 21 petals. Rows of seeds in sunflowers and pine cones always add up to Fibonacci numbers. Now, plants don't grow this way because they're receiving some kind of mysterious cosmic mandate. They're doing it because it's the most efficient way to pack as many seeds as possible into a small space. And if you want to see why that is, you can go watch Vihart's video, which is linked in the description, and it's awesome. But in addition to the numbers themselves, you also see the same ratio between Fibonacci numbers showing up. See, when you divide almost any Fibonacci number by the one before it in the sequence, especially the larger ones, you get the same number. 1.618 ... well, lots of numbers. The Greeks discovered this long before Fibonacci, and they called it phi. Today, it's sometimes known as the golden ratio. Phi was purportedly used by the ancient Greek sculptor Phidias to illustrate the idea of physical perfection. He's said to have used phi as a ratio between a statue's total height and the distance from the bottom of its feet to its navel, for instance, and also the length of a face divided by its width. There's a whole other set of patterns in nature that are based on what's called the golden rectangle, a rectangle whose side lengths are successive Fibonacci numbers like 8 by 13. This rectangle can be divided up into a series of squares whose lengths are also successive Fibonacci numbers, in this case 1 by 1, 2 by 2, 3 by 3, 5 by 5, and 8 by 8. When you draw an arc from one corner of each square to the other, they join to form a spiral that resembles many of the spirals we observe in nature. From the unfolding leaves of a desert succulent to the arrangement of those pine cone lobes and sunflower seeds and the shells of some snails. The math, you guys. It can be beautiful too.
Alright you guys, I hope you enjoyed this short video clip about the Fibonacci numbers and phi. So much for today, and I will see you in class.